Okay, so in this particular lecture, we're going to talk about inner product space. Inner product space. Yeah. So what is the inner product space? So before understanding inner product space, let us understand what is the inner product. So inner product is basically a function from V cross V to the field of V. Clear? What I mean to say is that V is a vector space. V is a vector space. Okay, a vector space over field F. A vector space over field F. Okay, so we define a function uv, a multivariable function. We have two variables, two independent values of this particular function. So the domain of this function is the v cross v set, and two its field. Okay, so this is the definition of an inner product, and it obeys certain conditions. Condition number one: uv is equal to the conjugate, variables reversed, uu, inner product applied on the same variable, same values, is greater than equal to 0, and uu equals to 0 if and only if u is a 0 vector. This condition is called positive definiteness condition. Positive definiteness condition. Number 3, u plus v w is equals to uw plus vw. Okay, this is called the distributive condition. And the fourth property is that au, where a is some value, some element taken from the field, it's treated as a constant, is v is equals to a times inner product on ub. This is called the linearity condition. Okay, so if there exists a function, elements of a vector space v cross v is mapped to f such that these four conditions are valid, then we say that uv is an inner product. Okay, is an inner product, and a vector space v is called an inner product space if there exists a function. Let us define it like this: from v cross v to f such that it is an inner product. Okay, so in very simple words, a vector space is called inner product space if it has a defined inner product in its cross domain. Is it clear? Let us go by some simple examples, then it will be clearer to understand. So suppose you take this vector space r on r, right? This is the field and this is the vector space r defined on r. Okay, here we assume the function xy such that this is equals to x times y. Okay, so clearly this function maps r cross r to its field r, right? Now this will be an inner product. We can check it very easily. So xy, which is written as x times y, is same as writing it as y times x, which is same as writing it as yx conjugate. The reason is the conjugate of a real number is a real number. That's basic. The conjugate of a real number is same as itself. It's very clear. Conjugate a plus ib has its conjugate as a minus ib. Okay, but any real number, so the real number is just remains unchanged when you find the conjugate. So the real number remains as it is. Okay, so is it clear? Okay, point number 2. So x plus y alpha. Okay, what is alpha? Alpha is an element taken from the domain r cross r itself. So we can write it as, it is x plus y times alpha. So this is x alpha plus y alpha. What is x alpha? X alpha is inner product this, and this is y. Okay, so distributive condition also holds. Number 3, I guess I missed the positive definiteness condition. This is equals to x square, which is always greater than equal to 0 for all x belongs to R. This is indeed the definition of R. Okay, it equals 0. It equals 0 if and only if x equals to 0. This is the simple definition of a real number. And number 4 point you have axy can be written as ax times y, which is by associativity can be written as a times xy, which is a times inner product of xy. Okay, so this function is indeed a inner product. Okay, extremely simple. We have got some more definitions, or sorry, some more examples of inner products. I'm not going to prove them. You can prove them on your own. So we are just taking them as an example. So example number 2, if you take the vector space Rn over R, okay, n-dimensional real number space over R. So here you have your elements as u belongs to V, implies u can be written in this form: x1, x2, and so on till xn, n elements, such that each xi belongs to R. Right? Achha. Now you define the function from V cross V to R such that uv can be written as x1 y1 plus x2 y2 and so on till xn yn, where you choose u as defined here, x1, x2, and so on till xn, and you choose v as y1, y2 till yn. Okay, so this is element time, corresponding element multiplied followed by addition. Okay, this will also be a inner product space. Very simple to understand. Okay, you can prove it on your own. One more example which you have is if you take V as the n-dimensional complex space over real numbers. Okay, this is also very simple to understand. Let's see. So suppose you take the vector space, suppose you take the inner product from V cross V to its field R such that, or let us do something, we can also choose the field to be C itself. Okay, we can also choose the field to be C itself. So let this be C such that uv can be written as a1 times b1 complement, sorry, not b1 complement, b1 conjugate plus a2 b2 conjugate and so on till an bn conjugate, where you choose u as a1 a2 till an and v as b1 b2 till bn. Clear? So since we have chosen the field to be C, so this must be C. Okay, so you take the elements, you find the conjugate and corresponding element multiplication followed by addition. This will also come out to be an inner product space, rather than inner product function. Okay, are these examples clear? Next we just see some properties of inner product space which are indeed important. So properties of inner product space. Property number 1, inner product of UAV. A is an element from the field. This is given as the A conjugate times inner product on UV. Clear? Got it? Now see, this is very simple to prove. I'm just giving the proof very simply. See, UAV can be written as the conjugate of AVU. This can be written as A conjugate times VU conjugate, which can be written as A conjugate times UV. Clear? Next property we see. So this is kind of an extension of this property itself. Inner product on U, BV plus CW can be written as B conjugate UV plus C conjugate UW. Clear? Number 3, inner product on 0 vector with V is equals to 0. Okay, is equals to 0. And one more, property number 4 we may say. So inner product on UV equals to 0 for all V belongs to the vector space capital V if and only if, or rather let this be a a one directional statement. U is a 0 vector. Is it clear? Is it clear? Or rather I can form it a biconditional statement if this property is known, because I wrote this one, so I am not writing this as a biconditional statement. So if U is 0, inner product is 0. If inner product is 0, then U must be 0. But the additional condition is that for all V, but this is also for all V itself. Clear? So these two conditions make the fourth condition a biconditional. Okay, this one is clear. Okay. Now the next concept in the concepts of inner product space gives you the term norm of a vector. Norm of a vector. Norm of a vector. Okay. So let us first understand the definition of what is a norm of a vector. So let V be an inner product space. Let V be an inner product space for any element from V. The norm which is in simple terms called the length, okay, length of a vector, norm of a vector of V is defined as root over of inner product of V on itself, okay, and is denoted as clear? So basically norm of a vector is equals to the root of inner product of V on itself. So this can also be written as norm of a vector squared is the inner product of V on itself. Extremely simple. Now since this is defined as an inner product, so it will follow all the properties of an inner product. Okay, got it? It will follow all the properties of inner product. Now let us still discuss some of the properties which are important properties. So we are discussing these properties as the using the norm notation. So we have norm of some inner product is always greater than or equal to 0. Okay, norm of a vector is equals to 0 if and only if the vector is 0. Point number 2, norm of a vector which is a constant multiple is equals to the constant taken outside with its mod times the norm of the vector. Number 3, which is one of the most important inequalities in mathematics, which we have already seen previously in our plus 2 levels and below that, which is the triangle inequality. So we have studied triangle inequality in the concepts of triangle itself, that the sum of two sides of a triangle is always greater than the third side. So the triangle inequality, what does it say? Let's see. The triangle inequality says that the norm of the addition of two vectors is always less than equals to the addition of the norm of the independent vectors. Okay, and this happens for all the elements in the vector space. This is the triangle inequality. Clear? Proof of the triangle inequality we will do later after we study the Cauchy-Schwarz inequality. Then we will be able to prove the triangle inequality. The first two proofs are pretty simple. See, norm of V is equals to root over of V cross V. So that implies norm of V square is equals to inner product of V cross V. Now norm of V squared equals to 0 implies this equals to 0. A square is equals to 0. Basically we are assuming this condition. So this equals to 0, and we know if this happens then V must be equals to 0. Okay, this is pretty simple. And also this is the inner product, so we know the inner product value always is greater than equal to 0. So this is a direct implementation of the inner product property. Number 2 is also very simple. So this can be written as alpha VV. Okay, clear? Sorry, my bad. Just misplaced the term. So this can be written as alpha V alpha V. So this is alpha taken from it comes out as it is, and from it alpha is taken out as its conjugate. So VV, and some element times conjugate is always its mod square, right? So this is root over of mod alpha squared VV, so which is mod of alpha times root over of inner product of V on itself, which is mod of alpha times mod of V. Okay. The third property, that is triangular inequality, we will prove later after we study the Cauchy-Schwarz inequality. So let us see the Cauchy-Schwarz inequality. We can understand it pretty simply. The Cauchy-Schwarz inequality. The Cauchy-Schwarz inequality is something of this sort. So let V be an inner product space. Let V be an inner product space for all elements of V. The mod of its inner product is less than equals to norm of each individual element. Norm of its inner product is less than equals to norm of its each individual element. Clear? Okay. For an example, we can use the concept of the real numbers. Okay. Suppose we choose V as R over R. Okay. We can define the inner product from V cross V to R such that, or rather, we take the, we can take the norm into consideration, or rather we can do it like this. See, basically in real numbers now, the norm of a vector is basically the modulus of it. So we can choose this as the dot product of the vectors. Okay, the dot product of the vectors. Now in real numbers, the norm of a vector is equals to the mod of it. Okay. Now what is dot product? So let us choose this. So dot product is this times mod of this vector times mod of this vector times cos theta, where theta is the angle between them. Okay. So if you place the modulus, so this is something like this. Modulus get distributed in the case of multiplication, so we can write it as mod of uv equals to modulus of u is modulus of u, modulus of v is modulus of v, and modulus of cos theta. Now we know mod of cos theta is always less than equals to 1, so this is less than equals to mod of u times mod of u. Okay, this is a simple example of what the Cauchy-Schwarz inequality gives to us. So let us see about the Cauchy-Schwarz inequality. The proof of the Cauchy-Schwarz inequality. Let's see. So suppose the vector is 0. Suppose u vector is 0. So that implies inner product on uv is equals to 0 as well. So mod of inner product is equals to 0 as well. Okay. This is pretty simple. Also this implies norm of u is 0 as well, which implies norm of u into norm of v is equals to 0 as well. So here you have the case of equality, which obeys the Cauchy-Schwarz inequality, right? Because you have the equality in itself. Okay. But suppose this is, say, case 1. Suppose u is not a 0 vector. Suppose u is not a 0 vector. Okay. Yes. So case number 2. Let u not be equal to 0. Now we choose a vector w such that it is defined as u minus lambda v. Okay. Now this, how we choose this vector is basically depending upon this constant lambda. So how we choose the lambda? Let us have a simple explanation of lambda. Okay. So suppose in R2, we have these two vectors x and y. Okay. U and v. Let's say. So let's say this is your u. Okay. Let's say this is your v, and let's say this is your u. Okay. So what you do is that you extend this particular vector. Let me make it a bit short. Okay. Suppose this is like this. This is v. When we extend this vector using a scalar multiple, the new vector comes out to be some lambda times v. Okay. Now what you do is that you try to take the distance between u and v. You try to take the shortest distance. Let's say the shortest distance between u and v. The shortest distance between u and v. So what is this resultant vector? The equation of this resultant vector. So it is u minus lambda v. Clear? It is u minus lambda v. Now, so mod of u minus lambda v will give you the distance. This distance. So this can be written as u minus lambda v times u minus lambda v. So which is something u square plus lambda square v square minus 2 lambda u dot v. Okay, u dot v. Now what we do is that we take this as a function of lambda. We take this as a function of lambda. Okay, so by the first differentiation you get this as 2 lambda mod of v square minus 2 times u dot v. Clear? So you are trying to find the minimum distance, so you need to minimize this. So let this be equals to 0, which implies lambda has the value u dot v over mod v square. Okay, so this is the value of lambda. Got it? So so now see, in reals this is what you have as the inner product space, inner product function as well, basically, and this is the norm of the vector. Okay, so we choose. So in our example, therefore, in our example, where we have taken w as u minus lambda v, we choose lambda as inner product uv divided by norm of v square. Clear? We are taking the shortest distance between these two vectors u and v, where v is scaled by lambda. Okay. Okay. Now see, since this is the inner product space, so we can define the inner product on w. So inner product on w. So this is greater than or equal to 0, which implies norm of w squared is greater than or equal to 0. Norm of w squared can be written as u minus. This is basically, so we could have done this directly from here as well. So from this statement we get u minus lambda v, is greater than or equal to 0. Clear? Now see, this can be distributed as, u times u minus lambda v minus lambda into v u minus lambda v. Okay, what we're doing is that we are taking the inner product with u and with minus lambda v, so minus lambda comes out as a constant and v remains inside as the first variable in the inner product definition. Okay, then we do the same with here. So here first we take the conjugate of 1. Conjugate of 1 is 1 itself. So this can be written as u minus lambda v u. Clear? U minus lambda v u. Then you take minus the conjugate. Okay, so this basically what you do is that you take this as the one. So from lambda you take lambda bar, right? From lambda you take lambda bar. Is it clear? So you have here lambda bar u minus lambda v 3 greater than equal to 0. Now you further distribute it. So this becomes u inner product minus lambda bar uv inner product minus this is lambda vu plus lambda bar vv. Okay, this much is clear. We do the same thing with here. So here you have, let us do one thing, let us not define it here. Okay, what we do is, what are we doing is that we basically, at a time we distribute from the first function itself, from the first function rather, I mean from the first variable of the inner product defined. Okay, so when we have already distributed, what I did wrong was that since I have already distributed this, so I can't, so this no more remains distributable from the second variable inside the inner product. Okay. So this is the final result you are getting, greater than or equal to 0. Yeah, now it's correct. Okay, now it's correct. So this is greater than or equal to 0. Now it's correct. Okay. Now from what here what you have is that, let's see. This uv can be written as, using the norm function, this uv can be written as, say this is norm of u squared minus this complete thing can be written as uv conjugate over norm of v squared times uv, because this lambda bar represents this particular value, minus again we put the value of lambda. So we put the value of lambda to get, this is uv over norm of v squared times vu plus lambda bar vv is greater than or equal to 0. Okay. Okay. Now so this lambda bar we can express this as, so see, let me write it down again. So this is norm of v squared minus uv bar over norm of v whole squared times inner product uv minus uv, and this vu can be written as uv conjugate over norm of v squared plus, see, this lambda bar can be written as uv over norm of v squared times uv conjugate over norm of v squared times norm of v squared, because inner product of v on v is norm of v squared. Okay, now see, this cancelled and the resulting value cancels this, right? Okay. From here you can write it as norm of u squared is greater than equals to uv conjugate times uv over norm of v squared. Now see, conjugate time it gives you the mod squared, right? So uv whole squared is less than equals to norm of u squared times norm of v squared, which implies mod of inner product uv is less than equals to norm of u. This is the Cauchy-Schwarz inequality. Is it clear? This is the Cauchy-Schwarz inequality. Okay. Now so let us take the, so from using the Cauchy-Schwarz inequality we can do the triangle inequality proof. So the triangle inequality. Okay. So what the triangle inequality says, norm of u plus v is less than equals to norm of u plus norm of v, right? Let's see. Proof of the statement goes something like this. Proof. The norm of u plus v whole squared is equals to inner product of u plus v, okay, which can be written as u, u plus v plus v, u plus v, which can be written as u plus uv plus vu plus vv. Okay, now see. So uu is norm of u whole squared, vv is norm of v whole squared, and vu is conjugate of uv. Now if you add a number with its conjugate, you get the twice of its real part. Okay, suppose you have a complex number a plus ib, okay, and its conjugate is a minus ib. If you add them, you get 2 times a. What is a? A is the real part of this complex number, so you can write it as plus 2 times the real part of uv. Clear? 2 times the real part of uv. Got it? Now see the real part of uv. The real part of uv will be less than equals to the mod of uv. Very simple. The real part of uv will always be less than the mod of uv. Okay, so if this happens, so we can replace this with, so from here we get norm of u plus v squared is less than equals to norm of u squared plus norm of v squared plus 2 times modulus of norm of uv, sorry, inner product of uv. Clear? You can take norm of a vector as the modulus of it. You can take the norm of a vector as the modulus of it. Don't care about that. This is pretty simple, pretty observable. You can do it on your own. You can check it on your own. Pretty much observable. Okay. So now by Cauchy-Schwarz inequality, by Cauchy-Schwarz inequality, we have the mod of u. Sorry, we have mod of inner product uv is less than equals to norm of u, norm of v. So we can put it here. So from here we get norm of u plus v whole squared is less than equals to norm of u squared plus norm of v squared plus 2 times norm of u, norm of v. So now this is equals to norm of u plus norm of v whole squared. So from here you get norm of u plus v is less than equals to norm of u plus for all uv belonging to the vector space. Clear? One more thing, let me write it down. One more thing. So note. In the Cauchy-Schwarz inequality case, where you had the mod of the inner product is less than equals to norm of u, norm of v. So equality is there. Equality exists if and only if u and v are linearly dependent. Okay, equality exists if and only if u and v are linearly dependent. Okay, just see. So for equality to exist, what we need to have is that norm of, so for equality to exist, what we need to basically have is that this must be equals to 0 for equality to exist, or we can say norm of this must be equals to 0. So which is a biconditional statement which says w is equals to 0. So w is equals to 0 means u minus lambda v must be equals to 0. From here you can see u is equals to lambda v, so u and v are linearly dependent. Yeah, because alpha is non-zero. and you are also having a coefficient of 1. Is it clear? The same thing also happens in triangle inequality case too. That in triangle inequality case, what happens? Equality exists if the vectors are linearly dependent. Same in the case of triangle inequality. Same in the case of triangle inequality. Okay. Equality exists if, we can check it on our own. Equality exists if the vectors are linearly dependent. In the next lecture, we will be studying the concepts of, we might be studying the concepts of inner product space and a metric space. Moving on to the concepts like orthonormal vectors and orthogonal vectors.